Hi, yes, we're back on the Lecroy oscilloscope PCB short/repair because I had so many people saying that they wanted to see the follow-up to this because I couldn't find the fault within the hour that I had last time. I'll link in the previous video if you haven't seen it. It is a must-watch. You can't. This probably won't make much sense to you unless you watch the previous video. So I thought we'd start again because we got to the point in the previous video where we found that we had a 0.1 ohm or thereabouts short across the 3.3 volt rail on here, and we tried to track that down, and I explained how the usual culprits are the either the bypass caps or one of the semiconductors or something like that. But of course I sucked off what I believe were all of the bypass capacitors on the 3.3 volt rail, and the short was still there. And then I did some quick thermal temperature measurements of the only 4 devices which seem left on the 3.3 volt rail, which are these ASICs here, because I don't have the memory modules plugged in, and they were all at the same temperature pretty much. So one of them didn't really stand out, that was hotter than the others, and I couldn't find any other place on the board, just using my hand, just a quick look, a quick feel around on the board to see if I could find any hot spots. But there has to be one here, because as I mentioned in the previous video, the 3.3 volt rail is only capable of 6 amps, the actual power supply, and we applied external 3.3 volts and we'll get in 11 amps. So that extra power has to be going somewhere and has to be heating something up. I can't do a Scottish accent, but you can't defy the laws of physics, Captain. It's got to be there. So there's extra power now. So there is definitely a short on this board. Contrary to what a lot of people said, a lot of people mentioned that, oh no, it's probably normal, and that power supply is capable of more, and they did all sorts of thermal, back of the envelope calculations to sort of convince themselves that that was the case. No, I can assure you, there is a short on this board somewhere, and that is obvious. A typical system rail on this board, like a typical 3.3 volt rail, will not measure 0.1 ohms both directions on a multimeter with different multimeters showing no capacitive charge up at all. That is just not normal. There is definitely a short on this board. And thanks to Sam at the Lecroy users group, there's a Yahoo users group specifically to these scopes, he measured the rail and confirmed that it was above 1 ohm. So there is definitely a short there. So let's find it, shall we? It can't be that hard. Now, it can't be that hard. Well, we'll find out, right? As I said, these heat sinks were all the same temperature. So what I'm going to do is I'm going to use an IR thermometer, and we'll go in there and we'll double check those, and we'll look around the board with one of those cheap IR thermometers, which everyone probably should have in their kit, and see if we can find something, because there's got to be something on this board on the 3.3 volt rail dissipating that extra power. Now, there's a few people who said, yeah, it might be some sort of latch up to another rail because I'm not powering the other rails and stuff like that. Well, yeah, that could be the case, but that doesn't explain the 0.1 ohms. And when you find a gotcha like that, you should track it down. That's why in the previous video, that's entirely what I focused on, because if you can't find that 0.1 ohm short, nothing else matters. So everything will be a red herring in terms of drawing the extra power. Now, it may be the case that there is some of that extra power dissipated in the other rails because it's going through protection diodes and stuff like that because we haven't powered up the extra rails, etc., etc. And that could be the case, but there is definitely some extra power being dissipated there. So I expect there to be something else on this board that's heating up. Now let's just do a quick recap here. I've got my external high current supply at 3.3 volts. It says 3.2, but it's near enough to 3.3. And it's drawing about 11 amps, which, yes, if you take the 0.11 ohms short, it should be drawing a lot more than that. And people said, there's something wrong there. But no, it is a short. That is very common and expected in something like this. You would expect the resistance to heat up and have a temp code like that. It is very, very common, and then the currents drop. Just because we measure 0.11 ohms at, you know, the milliamp or 2 that this multimeter is going to measure that current at, doesn't mean that resistance is going to stay the same at 10 or 11 amps. It's not. So I would expect it not to match up with Ohm's law in that respect, because the short is going to be non-linear and in some respect, and or it's going to have a temp code and it's going to heat up. So that is perfectly normal, so don't worry about that. Now, a few people wanted me to measure the voltage over here as well. I don't think we'll get too much drop in those leads, maybe a few hundred millivolts. Let's have a look. There you go, 3.05 volts. So really, you know, it's not a huge drop. It's not a huge drop there at all. Now, I've only had this thing on for a minute or two, but let's have a look at the temperatures of these heat sinks again. I've got my little Fluke 59 mini IR thermometer here, and that will tell us the temperature on those heat sinks. Now, I think I was getting around about 70 degrees or something before, after they heated up for quite a few minutes. And yeah, I have no idea if this is regular operating temperature or not, whether or not the clocks are working, whether or not you need the other power rails powered up, whether or not you need the processor board. It doesn't matter, okay? We're looking for a temperature differential between these heat sinks. So let's measure that. You know, it's going to peak at about 60 there. That one's very similar, around 60. This one here is, yeah, it's around 60 as well. If I can get it, yeah, 65. So there's not a huge, there we go, 63. You know, it's quite hard to get it with these things, but you know, I would expect one of those to stand out. So really, there's no temperature differences between those. Forget it, completely rule it out. Now, let's probe around other parts of the board and see if we can find it. Let's take the bench, for example, as a reference. It's 20, you know, 24, 25 degrees, for example, 27. I mean, we're going to get some heat coming off the heat sinks and stuff like that. So, as I said before, I don't think any part of all this stuff is powered up at all. So really, I wouldn't expect to find, and these, once I think just we're getting some residual heat from those heat sinks there, but these ASICs of course aren't powered up. Now there's one thing I wanted to check, because we really have to go back to the beginning here. We have to go back and consider that it could be a physical short. Now, in the first video I ruled that out, because that is usually the least likely scenario for a product like this that used to work just fine. It was out in the field, worked for years. You know, they don't just magically get a short in the power plane or a connector or something like that. But I want to go back and start at the connector here and have a look. Now these, there's no surprises for guessing that these alligator clips here get reasonably warm, because there's contact resistance in there. So this thing's working at 11 amps, so they get quite warm. But maybe, you know, if there's a short near it or under the connector or something like that, as unlikely as it seems, we have to consider that, because this unit has actually had some physical shock or something to it. If you've seen the teardown of this, you'll know that the case has got a big crack in it and all sorts of things. So it's most likely been dropped or something like that. So maybe we've got some stress transferred onto the connector, or possibly, as a couple of people mentioned, the mounting hole down in there. So possibly there could be a short in there. Look at that. We might be getting some residual heat from the connectors there, because those connectors are quite hot, right? They're like 40 plus degrees. They're getting quite warm because there's a fair bit of contact resistance in there, so it's going to heat up. So, but that board next to it is getting quite warm. Hang on, 35 degrees and climbing on that pad down there. Look at that, 32. Maybe there's possibly some heat spreading through that ground plane. possibly, even all the way over to here, because I wouldn't expected that to be warm at all over there, but this one over here is definitely hot. There's something going on there. If you design this board properly, and these large mounting holes here, you should have a power plane pullback, what's called pullback, from around the holes, so that when you put screws in there and you tighten them all up, then it doesn't crush the power planes inside there. But who knows? Unless you had the CAD files for this thing and can check, or you dissected it, or you x-rayed it, or something like that, you don't know how close those are. So it's not out of the the bounds of possibility that when this thing was dropped, there could have been pressure on a through hole, a mounting pad like that, and it could have crushed the internal power planes. This is a 6-layer board, so there's not going to be a huge physical difference, a physical gap between the ground plane and the power plane. So it depends on what layer the 3.3 volt one's on. Usually it's going to be right next to the ground plane. So with a very small amount of FR4 pre-preg between the layers. So it's not out of the bounds of possibility that you could crush that due to something like that. So what can we do to test that theory that it could be something to do, some sort of short on the power plane in there? Well, we can freeze it, we can cool it down and see if the current changes. Heck, it might even go away. If you freeze it down enough, the short could actually vanish. So if we're right, we might actually see that current change. Now, I don't have any freezer spray, but I do have air duster. So what you do with the air duster is simply turn it upside down, and all the cold gas actually settles at the bottom, and that comes out. Instant freezer spray. Cool down that pad and see if this current changes. You ready? No, nothing. It's not changing at all. That's strange. Would have expected something. Maybe our theory's not correct. You can actually see how it's freezing down in there. It really is, that is pretty darn cold. And if I get the thermometer on that again, 16 degrees, 13, 8, it is very, very cold. That pad is now very cold, but it's still showing 10.5 amps. Now here's that pad up close, and I don't see too much, well, really any major compression trauma or anything like that on the pad. Well, and the same goes for the bottom there. I mean, it's not like somebody's like really screwed this thing up and compressed those. That looks pretty darn normal wear and tear on those mounting pads to me. So possibly in the connector. I don't want to have to desolder the connector unless I absolutely have to. Now they look okay, but of course there could, it's a remote possibility, but we're getting down to that point where we have to look at remote possibilities. Now I just thought I'd check something. These mounting holes that we're curious about to see if they're actually grounded. So yes, they are actually grounded. There you go. Right, so if there's not adequate plane pullback inside those things, they could certainly, compress or short out or something like that with physical damage. Now I think we've gotten to the point where we probably have to power up the other rails as well and just see what our current draw is on that 3.3 volt rail. And yes, I've measured it, and this 3.3 volt rail does seem to be dead on this power supply. So the power supply seems to have died. As I said in the first video, it and the teardown, of course, it was actually working, and then it died. So I suspect that the short eventually killed the thing. Now, this is my theory on this. There is definitely a short on this board, okay? 0.1 ohms is not correct, right? It's just not. There is definitely a short there. And the power supply was good enough to continue to keep the thing basically working, but we were getting corruption on that 3.3 volt rail, i.e. all the capture memory, which is kind of what we were seeing in the data. So all of the capture memory which runs from the 3.3 volt rail, there's probably excess ripple or whatever was going on there. It was hiccuping or doing whatever, I don't know, but it was so it was able to still power through that short, just like our high current supply here can. It can still supply 3.3 volts, but it was drawing too much, and it eventually got to the point where no, I can't take this anymore. Kaput, it's dead. Okay, so what we're going to do is but I have measured all the other rails and they all still work, so I'm going to cut into this cable here, the 3.3 volt one. We'll power that from the external supply, and we'll power up all the other ones as well and see what we get. Right, so what I've got now is I've got it powered up, and we'll check the voltages on here. 5 volts, there we go, and we're getting -5 volts. So all the other rails are all up. Not exactly sure what they are, +15. So the other rails are up to +5 and all that. But look, it's still drawing 9.6 amps. So there you go. That's busted that theory that it was, latching, the power was latching into other unpowered rails through protection diodes and, all that sort of jazz. So my hunch was correct that there definitely is a short there. And it's not surprising because 0.1 ohms is not normal. Now, Sam has also confirmed that, yeah, the 3.3 volt rail should be drawing about 6 amps. So it is, and he also said, as I said before, that it's, it's over an ohm on, when you actually measure it with a multimeter. So there is definitely a short on this board. No doubt about it. Don't want to hear any more. And just to doubly sure, yes, I've plugged in the processor board here, and yes, we're still drawing 10 amps on the 3.3 volt rail. I just want to try this temperature again, but I leave the connector in now so that we've got the 2 pins going through to the power plane there. The third one seems to go off to somewhere else, and also I'm using the ground point over here, so we should get less heating on that pad due to the contact resistance we had before. So we're still 33 degrees on that pad down in there. So whether or not that's actually normal due to the contact resistance of the connector at 10 or 11 amps, and then the heat is spreading through the power plane. See, because even this pad right down here, well away from the ground point over here and the contact resistance over here is still, that's still 33 degrees. So clearly that's just the residual heat spreading through the power plane. So it is not obvious yet where this damn short is. Now, a few people ask, why don't I use my AIM TTI iProber 520? It's because it's not really going to work. You're going to get positional issues, as I was showing in the video for this, rotational positional issues on this sort of thing. So if you put it here, okay, I've got it into the multimeter instead of the scope because we're dealing with DC here. It's just fine. And if I rotate that, look at just the positional different, like I'm just rotating that, okay? So just the idea, rotating that is going to be all over the shop. There, you're pushing the brown stuff up the hill with a pointy stick, trying to use this thing. I'm afraid it's not going to work. You could do it like using an AC method on the rail or something, but no, ugly. So it's just simply not going to work when you have a huge power plane like this thing. So no, sorry, as cool as this thing is, it's not going to do the job in this particular instance. Now, as I mentioned before, you can do the thing with like feeding constant current through the thing and then using this to measure voltage drops. But the problem with that is when you've got active devices on here drawing huge amounts of current, you're naturally going to get the drops across here anyway. So, you're going to get the drops across the plane. So here's our input connector, and all these 4 ASIC devices here are all drawing, you know, large amounts of current. So unless you could isolate those, it's going to be incredibly difficult to find the issue. Like, let's go from this cap here, for example, to this one. I think I got the right one. No, the other pad here. Okay, so just from one ASIC to the other, we've got a 13 millivolt drop there, okay, from there to there across the plane there, okay, 13 millivolts. And then if we go a bit more, we'll find that we've got more drop. Oh, wrong pad. There we go, we've got 40 millivolts drop across there like that. And then if we go over here, we're going to get a larger drop. Oh, if we can get in there, there we go, we've got 81 millivolts drop. So, you know, how can you really essentially narrow that down when you've got such large currents drawn across a plane like that? It's very difficult to do. So I don't think that's really going to work in this particular instance. It can work in other instances, but this one, not so much. So we can do the same thing again with the, instead of the drop on the rail itself, we can get the voltage drop of the rail instead of the voltage drop across the resistance of the tracks and the plane. So we can start out over here, and we're getting at the connector, we're getting 3.032 volts input, okay? 3.0325 for example. And then let's go to our cap over here. Bang, it's dropped a bit. You'd expect that just due to the plane resistance. Then we'd expect it to drop a bit more. There we go, 2.96. As we go to this ASIC over here, 2.93. There you go. It is dropping as you progress across the plane like that. What does that tell you? Nothing, essentially. Now if we scan over the board with our IR thermometer again, we can have a look, you know, 61, 63, it sort of peaks out at 64, 63, similar sort of peak in 65, peak in there. So, you know, there's nothing in that really. Go to the other ASIC, 63, you know, that's got slightly more heat sinking on that one, I think, so you'd expect it to be a little bit lower. But yeah, you know, like there's not much in that one though. Is only, oh no, there we go, we can get it going up to almost 60, something like that. So, you know, very similar temperatures across the board, and it drops as you go away, for example, pretty evenly. As I said, that temperature is going to be, you know, fairly evenly spread across that plane. So trying to detect this is almost needle in a haystack. So this thing just doesn't seem to be doing the business. I mean, it's only a single spot. What we need is resolution. Unfortunately, I don't have one of those multi-$1,000 thermal IR cameras, but I know someone who does. Let's go. So, thanks to my mate Charles at Trio Smart Cow, purveyors of fine test equipment pornography, I have just that. Check out these puppies. I've got 3 infrared thermal imaging cameras. Fantastic. We have a Flir E60. This puppy goes for about $12,000. It's 320 by 240. It's pretty much the Rolls-Royce in handheld thermal imaging cameras. I mean, Flir are the best in the business, and the E60 is the top of the range E-series. Oh, beautiful bit of kit. And check out this, folks. Look at this. Made in Estonia. Woohoo! Would you believe it? There you go. And then we have a UL Vision brand TI 160. These are much cheaper, doesn't have the same resolution as you know, the Flir, of course, but still this one's much cheaper. I think Charles said this one's about 2,800 Australian dollars or something like that. Don't fully quote me on that. And then we have the same brand again, UL Vision TI 395. This is I think a couple of $1,000 more expensive than this one, and it's a gun style one, and it's almost identical look and feel to the Sanyo Exacti camera I used to use for the blog. Check it out. It's like, you know, it's these gun style ones, almost identical look and feel. Oh man, I love it. So that's a nice little funky form factor. I don't really like this form factor on here. In fact, I'm probably, after I finish doing some thermal measurements of this, I think I'm going to do a separate video just playing around with this thing, these things. So I've only got them for the afternoon, so I'll have a further play around with them later. But what we want to do now, we've got the right tool for the job now, folks, because this board, if you remember, just a few minutes ago, was, we couldn't find that any hotspot at all, apart from the ASICs. We couldn't find it like around the hole down there and the wires and stuff like that. It seemed to be fairly evenly spread around the power plane in this thing. So let's power it up, and let's say start out with the Rolls-Royce. Let's use the Flir E60 and see what this puppy is capable of doing. Welcome to the world of infrared, Flir. Oh, just want to hug this thing. Oh, it's pornographic, it really is. Oh man, what a great toy. Let's start out by taking a look at our heat sinks. Ta-da! Here we go. And if I this is the focus on the front here. So if I adjust the focus, we can see the temperature, and you can see the spot measurement up there. We're talking, 75 degrees, something like that. I mean, this one's only 79, but this second heatsink here seems to be much, well, by much hotter, I mean, 3 or 4 degrees hotter than what we were getting, than what we get on the other ones. And considering that this one here is the same heatsink, so it seems to be a few degrees hotter. And this Flir camera has various different modes, of course, which we need to investigate and look at. But so that may, I don't know if that says anything about my original prediction in the first video, that that second device there seemed to have a slightly lower resistance than all the others. So maybe it's no surprise that it's getting hot, but check out the resolution on this thing. It really is very, very, and I can take screen captures of that and all that sort of jazz. So right, so we know that those heat sinks are all pretty much identical temperature, except for the second one there. Now if we scan around the board, we can see our connector down there. If you have a look, I've got the I'm deliberately not putting it right on the pins there. I'm deliberately getting it away so we can look at the current flowing through those wires with the thermal imaging camera, and also we should see a hotspot around here where it's connected. But let's see if we can find a hotspot on there, and in particular that mounting hole down in there. So if we take a look around, there you go, you can see the connector, and you can see the heat spreading out from that connector there. I mean, that connector is getting up to 42 degrees. It is actually pretty darn hot. Now if we have a look at the connector there, we can actually see, you see how the two right hand wires there are like that one, it's like 40 degrees on those wires, and the one on the right hand side that I said had no current flowing through it, or very little current, you can see that there is no current flowing through that other wire. Now it's tricky to sort of get this because we are getting heat spreading from this heatsink here, so it is rather a bit tricky. It spreads across, but you can see that there's no hotspot on that hole, mounting hole down there at all. There is no hotspot. So there's nothing going on there. You can actually see inside the actual connector as well. If you can see inside that, there you go. You can actually see the connections heating up inside the connection, but no hotspot on that mounting hole. So that pretty much rules that out. There you go. So it is not the mounting hole, which a lot of people thought. In fact, the short doesn't seem to be anywhere else on this board. I can't see it. Now I can't see any other hotspots around the board here. Sorry, it's hard to really get this thing on camera, but there are no other hotspots apart from those 4 heat sinks. And of course that second one, which we'll call the second one down there, does look hotter than all the others, but there's like nothing. I can't see anything. There's no other components that actually show any hotspots at all. So this is not looking good, folks. Let me tell you, it is looking like it is something to do with those ASICs. Now, if we pan around the rest of the board, now here's an interesting thing. You might see a hotspot on these B and C connectors here, and you might think they're actually hotter than other parts of the board, but that's not. That's just heat reflection, and you've got to be very careful with shiny objects like this. You will actually get heat reflection off these components. So if you don't use it correctly, you might think, aha, that B and C is getting hot, but it's not. It is just reflection. If I put my hand near that, you'll see it change, right? There you go. If I put my hand near that, you can see the heat reflected off those shiny B and Cs, and it can also do the same thing on solder joints and things like that as well. So that's a real trap for young players with using these things. You've got to know about the reflective properties you're actually viewing. Now let's have a look at the back of the board, see if we can get it, and you can see the hotspots on the ASICs there, of course. That's about 65 degrees on the back of there, and yeah, that's the first one. And the second one, 67. So once again, it's a bit hotter. Third one, not 65, not quite as hot. And the fourth one down there, but there are no other hotspots. I mean, there's the connector down there, right? It's showing nothing around that mounting hole. Let me get that in focus. That's the mounting hole down there. And I can't see anything, any issue there whatsoever. If you go up here, you can see the connector up there. You've got the ground clip, but no, nothing. And of course, no other part of the board is powered. Now here's another example of one of these traps for young players. You might think, aha, look, we've found right in the center there a little hotspot. It's a couple of degrees hotter, and it certainly shows up there, but it's not. What is it? It is these shiny solder pads here. They're the things that are showing up on there as a different temperature because they're shiny. It's not because they're actually warmer. So yeah, when you're using these things, just make sure you really know how to use them, because there's quite a few traps in there. But no, sorry folks, this $12,000 piece of magic is telling me that there is nothing wrong with this board at all in terms of actual shorts on the board. And if we use the UL IR Vision camera as well, we get, well, the same result. I mean, I can scan over the board again, but there's the connector down there, if we're going to have a look at that. And once again, there is no hotspot on that hole at all. You can see the connector. Not sure why it freezes there. It says rectifying. There you go. You can see the two wires heating up. Look, that works brilliantly actually. And you can see this one has a tracker. Well, the Flir has it as well. It has an auto hotspot tracker which tells you the hottest spot on the screen there. But you can see the two wires on the right hand side have all the current flowing through it. The one on the left has bugger all. It's just getting some residual heat from the others as we measured in the first video, and there's nothing on that hole at all. There's nothing there, and if I scan the rest of the board, there's nothing over the board either. Once again, hard to capture on camera. I've done it off camera and thoroughly, and there's nothing there. Zip. Now if I switch the other power rails on here, you'll notice that it dropped from 10.4 there to 8.6. So it looks like there might actually be some current going through the other unpowered rails there, either through protection diodes or whatever mechanism is in place on those rails to actually do that. So, but still, you know, that doesn't explain anything. That's a complete non sequitur. So all that's left is to current limit this and see if we can get any temperature differentials, but I reckon all those are dead. Now I'll have a quick scan around the board again with just the 3.3 volt rail, and as you can see, apart from the heat sinks and the connector, I've only just switched it on. Everything else is dark apart from those heat sinks. So let's switch on all the other supplies, and we should start seeing a few other things heat up as well. So yeah, I can start to see some other circuitry on the far side. Yeah, look, you can see all those chips on the far side there start to heat up because they're all the 5 volt rail stuff. You can see they weren't lit before. This thing has a laser on it too, by the way. You can actually switch the laser pointer on and it does show up, but there's some parallax error there on this thing, so it's not that great. But you can see some of the other chips in there heated up. Another one over there is getting a bit warm, 47 degrees. And but yeah, not that exciting. There we go, that one in there. There's another, that one in there is getting quite warm. It's getting up to 73 degrees. That one behind there, that's really quite warm. Yow, ouchie. Now this is interesting, check this out. I've got a constant current of 1 amp over here. So there's my constant current, and the voltage has dropped right down. Of course, it's no longer 3.3 volt. It can't provide all the, well, it's current limited, that's why. And if I switch on all the other rails, check out this little chip. Gets hot really, really quickly. He gets up to 100 degrees, but I don't think it's faulty. It's just that the fact that that voltage on that 3.3 volt rail has dropped, because that goes away if that 3.3 volt rail actually goes up to normal. So yeah, well, I mean, I've checked that chip's actually connected to the 5 volt rail, but obviously there's something on maybe the inputs or something like that that's causing that sucker to heat up. And if I turn on all the other rails without the 3.3, check out the hotspot inside those chips. You can actually see the dye heating up through the plastic package of that. That is really quite, that's really quite something. I like it. And once again, that chip over there is getting red hot as well. That's if you don't power the 3.3 volt rail. So those chips really do not like that at all. And with the power supply current limited on 1 amp, you can see the ADC heat sinks over there are still warm, and you can see once again that that second ASIC we've been looking at is still warmer than all the others. So, but you know, that really doesn't account for all of the difference in the power. If these 3 chips were working and this one was faulty and somehow got SCR latch up or some other damage internally which shorted it out across the power rails, then, well, I'd expect it to be massively, a massive temperature difference compared to the others. But as it stands, it's only a couple of degrees. So really, there's nothing in that. Well, sorry folks, I think that's all I'm going to do on this one today, because I think I'm going to call this one and declare it unrepairable. I think something has died in this power supply, which has killed, taking out everything on the 3.3 volt rail, everything being the only 4 devices on the 3.3 volt rail, which are these 4 ASICs here. Unless somebody can come up with another very plausible explanation for what's wrong here. I mean, I cannot find a hotspot where it's you know, dissipating all that extra power. We know for a fact the rail's not supposed to be 0.1 ohms. Obviously, it's supposed to be an order of magnitude greater than that. We know it's not supposed to take 11 amps. We know it's only supposed to take 6 tops. So all that extra power is going somewhere, and we've used a $12,000 IR thermal camera, gone all over this thing, and cannot find a hot spot at all. All the power is being dissipated in these 4 ASICs. So and because they're almost essentially a uniform temperature, the only logical conclusion on this one, folks, as much as I hate to say it, I think it's unrepairable. 4 identically dead ASICs. That one slightly more dead than the rest. I might have some more fun with it, maybe, I don't know, maybe suck out this second device and see if it makes a huge amount of difference, but nah. Think we've got a loser, folks. Bummer. Anyway, if you want to discuss it, jump on over to the EEVblog forum. Catch you next time.